hope everybody had a good and somewhat relaxing break and is ready to go here in the new year. I guess, yeah, a quick announcement about the change of time and location. This will be the standard time and room now for this semester. If anybody is aware of any other course conflicts with any of the graduate courses, please come talk to me afterwards, and if it's only 1 or 2 students, perhaps we can make an exception there. But yeah, this is now the regular time and place for this semester. And this is a required course for graduate students, so please do try to make it to all of them that you can. And then if you're going to be away, please let me know in advance. If it's for academic reasons, that's totally fine. We'll get a letter from your supervisor, and that's fine as well. So I think that's that. We're going to try something a little bit different as well. Catering services now offers pizza, so we've ordered that for today, and we've had that scheduled for delivery at the end. Let me know how it goes, if it's good, bad, or indifferent, I guess. And we can maybe try to switch it up between the pizza and the wraps going forward, or just pizza if it's a hit. So give me feedback, I guess, and we can go from there. I think then, without further ado, I'd like to introduce today's speaker. So we have with us Dr. Daniel Flores Tapia from the University of Manitoba. And Dr. Flores Tapia completed his undergraduate degree in electrical engineering from the Monterrey Institute of Technology in Chihuahua, Mexico, and then came to pursue his PhD here at the University of Manitoba and completed his degree in electrical and computer engineering in 2008. After that, he undertook a postdoctoral fellowship at the Cancer Care Manitoba in their Division of Medical Physics. And since then has been working as a research associate in the Department of Physics and Astronomy, working closely with Dr. Stephen Pistorius. And yeah, so Dr. Flores Tapia has published over 50 papers and conference proceedings and received multiple awards and grants for his work. And today we're very glad to have him tell us about his ongoing research dealing with microwave radar as a novel approach for breast cancer detection.
Thank you, Dr. Figley. Good afternoon. I'm going to talk this afternoon a little bit about the work that we're doing in the Department of Physics on the development of microwave radar for breast cancer detection. As of today, breast cancer is probably the second most diagnosed type of non-skin cancer among women. And in 2011, 1.5 million women were diagnosed with this disease. As in with many other types of cancer, early detection and treatment are crucial factors to improve the subject's chances of survival. Right now, the gold standard for breast cancer, for early stage breast cancer detection, is X-ray mammography. Nevertheless, this technology is very sensitive. It means that it catches lesions on the breast at very early stages or small sizes. But the problem is that it is not very specific. It's subject to the skill of the practitioner to see if the lesion that was detected is actually malignant or benign. Due to this, the lack of specificity can lead to increased number of unnecessary biopsies. I prepared this small table just to show you how the most prominent breast cancer detection techniques stand at this moment. In the first row we have mammography, which has a very high sensitivity. It has average specificity. By specificity, of course, I mean its ability to discern between malignant and benign lesions. It's very comfortable for the subject due to the fact that it requires breast compression. And the cost of this technology is in the range of $100,000 to $500,000 in average. In the second row, we have magnetic resonance imaging, which has a very high sensitivity. It has an average specificity that can be improved with contrast agents. It is very comfortable, well, mostly because no compression is needed. The only issue with MRI is if the subject is claustrophobic, that can be an issue, but the cost is very high. An average MRI scanner can go as low as $1 million. In the third row, we have ultrasound, which is not very sensitive. It's not as sensitive as the other two technologies, mostly because acoustic waves do not propagate through greater depths in dense breast tissue. Nevertheless, it is very specific. Its comfort is quite low, mostly because the breast will be compressed as well during the imaging procedure, but it's very, very cheap at the well compared to the other two modalities. Portable ultrasound scanner can go for as low as $20,000 to $30,000. In the last couple of years, there has been an interest in the medical imaging community on the use of microwave imaging for breast cancer detection. This technology has a number of features that make it very desirable from the clinical point of view. When I give these talks, whenever I go to a conference or I present a seminar, people usually associate microwaves with a microwave oven. They make the assumption that we use similar powers of power. It is not actually true. The average microwave oven runs with a power of 300 watts. The power levels used in microimaging technology is in the order of 1 dBm, which is roughly 1/5 of the power that a conventional cell phone uses. So it's a very, very small, small power waveform. Another point that goes well with the clinical staff is that it's comfortable for the patient. No compression is needed due to the fact that the systems developed for microimaging share many components with common equipment used in communications and cell phone technology. The cost is quite low because you need nothing more, well, when you develop everything from scratch, of course, than a couple of RF circuitry and amplifiers. And most importantly, due to the fact that it is low power, non-ionizing waveforms, the danger of prolonged exposure is minimal. And currently there are two main modalities when it comes to microimaging. My colleagues at the electromagnetic imaging group here at the U of M provided me with this nice image corresponding to the first modality, which is microwave tomography. In microwave tomography, essentially, you irradiate the breast with a single frequency waveform. Then you collect the responses at a series of points around the breast, and then you use that information to guide an optimization process that essentially produces an electric map of the breast. The result of that electric map is actually two images: one that corresponds to the permittivity of the breast, and a second image that corresponds to the conductivity of the breast. Why is this important? Well, microimaging is based on the contrast present between malignant and healthy breast tissues, which, according to the latest in vivo studies, is around 2 to 1. This is a significant difference compared to the contrast of X-ray absorption that is currently the physical principle used to X-ray mammography, which is in the order of 10%. So in theory, when we use microwave imaging, we should be able to get images with higher contrast than the ones obtained in conventional X-ray mammography. Mostly due to our interest in the last couple of years, and the non-ionizing group at the imaging group at the Department of Physics, we're dealing with the second modality, which is ultra-wideband radar. This is an electromagnetic equivalent of ultrasound. What we're trying to do here is irradiate the breast region with ultra-wideband waveforms. We collect them and process them to obtain an image of the different dielectric interfaces on the breast, which essentially give us a map of the locations in which the high reflectivity objects are shown. For example, in this photo, we have a synthetic phantom that we developed our lab. The green patches are a synthetic compound that we use to emulate dense tissue structures. And the circle is moved. And here we have a glass bubble, which is filled with a mixture of fructose and water, which emulates the dielectric properties of breast tumors. And as you can see in the reconstruct image, the most prominent response of the image corresponds to the synthetic tumor that is on the experimental setup. Best microwave radar is a fast and simple way of trying to get a qualitative image in which breast tumors can be visualized. Basically, there are two main protocols to record breast microwave radar signals. In both of them, you define a series of locations around the breast. In the first protocol, which is a monostatic scan protocol, you scan using the same antenna. You use the same antenna as a transmitter and a receiver. From an initial scan location, you irradiate an ultra-wideband waveform. The ultra-wideband waveform propagates to the breast. Then the responses from whichever breast structures are inside the breast come back to the antenna. You record them using your RF system, and then you move the antenna to the next scan location. In a static protocol, basically you do something similar. The only difference is that you irradiate using one antenna and receive using a different antenna. Each one of them has its advantages and disadvantages. The monostatic scan protocol allows you to form images using a minimal of a priori information, whereas the bistatic scan protocol has enhanced capabilities to differentiate between healthy tissues and breast tumors. This is work far from over. Currently, the biggest issues in breast microwave radar is the fact that most of the images present contrast to noise ratios in the order of 1 to 2 dBs. There's reduced specificity due to this. The image reconstruction times are quite low. It can be as low as 5 minutes, and that's for a single plane. When you're collecting a three-dimensional model that is around 10 to 15 planes, as it is in the majority of the clinical systems right now, the reconstruction process can go up to for an hour. And right now, it requires mechanically complex systems, especially because most clinical systems require the use of matching fluid. Why is matching fluid needed? Essentially, the principle is that the matching fluid allows the electromagnetic waves to have better propagation inside the breast. Similarly to what is done in ultrasound when gel is applied to the area that is imaged. Basically, the gel allows the acoustic waves to travel further into the tissue. So the goal for a project during the last 5 years is to develop a clinical system for breast cancer detection which uses microwave radar. This system should be able to detect lesions, ideally as small as 5 millimeters. Why 5 millimeters? Well, it is consensus in the breast cancer epidemiology community that if you can find a tumor when it is 5 millimeters, the average patient chances for survival in a 5-year interval is 99%, which means that that patient is very likely to die from causes related to that tumor within the next 5 years. We are working on two main areas at the moment. The first one is breast microradar imaging. Right now we're focusing on the development of 2 and 3D image reconstruction algorithms. Our particular technique that we have developed in-house is called radar holography. We are also trying to solve the issue of the execution time regarding the reconstruction time, the reconstruction time. We're using general purpose graphical processing units for this objective. We are trying to get rid of some of the a priori information that you need to form a breast microradar image using autofocus algorithms. And we're trying to develop a full clinical system that can be used to test our techniques developed in-house. And a very recent area that we have in the study is the use of, is the detection of breast tumors using breast microradar sensing. In this particular project, we are not using an image, we're using artificial intelligence techniques to try to determine if a particular set of breast data contains a tumor. The main goal of this project is to develop a portable system that can be used in remote or thermal country communities. Well, this is a block diagram of the algorithm that we have been developing during the last 10 years. It's called microwave holography. For those of you that have worked in MRI, it uses case-based processing techniques very similar to what they are to how magnetic resonance images are reconstructed. Right now, the majority of the breast microradar algorithms are thought in the sense that the reconstruction is only done in the time domain. They use beamformers essentially, which for this application they have a number of limitations. For example, you need a significant amount of a priori information, including the nature of the antenna radiation pattern in the breast, which is not easy to estimate, especially when you have the kind of variability on a clinical environment, such as what you will expect when you see different subjects and you have no prior information about the breast anatomy. So what we did, we thought, what about if we reconstruct the data based on the properties of the signal in the frequency domain. So the first thing we do, we calculate the Fourier transform of the recorded data sets. Basically, in the frequency domain, there's a parameter that every reflection that we collect from the breast has, which is called instantaneous frequency. We can use a series of mathematical models to migrate the reflections recorded at each scan location from the location where they originally appear in the dataset to the location where they are with respect to the center of rotation of our system. All this is done using the particular instantaneous frequency of each response. The first thing we do, since the fact that the data is a function of time, of signal travel time and angular location, we need to migrate it from that domain in which the origin is the scan geometry, in effect, to a domain where the origin of our system is the center of rotation of the scan geometry. For that, we perform a match filtering process. Then we coherently add, using the different instantaneous frequency values along some trajectories in the case space that are called the the isodoppler contours in order to migrate the signals from their locations in the original data set to the locations where they are with respect to the center of rotation. Since this image is a function of the signal travel time and alpha and and theta and I don't know how to pronounce these letters, sorry, which is essentially a three-dimensional polar domain, we need to translate it to a Cartesian system of coordinates, since that's the space where we're going to visualize it. So we perform a non-linear mapping using basically the polar transformation theorem in the frequency domain. After that, since this mapping is not linear, we need to perform an interpolation in order to use conventional Fourier techniques that allow us to convert that frequency domain data back into the spatial domain, which will show us the location of the high reflectivity regions. We have been working during the last 4 years on the development of a clinical system, and for this purpose we wanted to develop an in-house antenna that allows to operate in the 1.5 to 6 gigahertz bandwidth. Why this bandwidth? Mostly because we wanted to improve the penetration of the signal into the breast. As you go higher in the irradiated signal bandwidth, what happens is that the breast tissues present a higher degree of absorption, and in order to improve the quality, we wanted to stay low. Another thing that we consider during the development of these techniques and the development of our system is that we will be dealing with phantoms and ultimately with subjects that will have a considerable amount of dense tissue in their breast, or we have to include a significant amount of dense tissue in our phantoms. This is a common problem in the breast microvibrator, as most of the early stage algorithms are validated using only a fatty model in which only a tumor is included. When we compare the dielectric properties of fat and tumor, you have a contrast that can range between 10 to 1 to 5 to 1. This is not a realistic scenario, mostly because the vast majority of breast tumors are invasive ductal carcinoma, which means that the tumors originate from the ducts in the breast. The ducts are essentially structures that are connected to dense tissue, and due to that fact, you're going to have very little contrast between the tumor and the adjacent structures. This afternoon, I'm going to show you some results that we have obtained using the phantom that we call at the lab, the 3 o'clock, 6 o'clock phantom. Mostly because we have dense tissue structure at 6 o'clock, another dense tissue structure at 3 o'clock using clock nomenclature. And we introduce we perform five experiments. One without any tumors, and one with a tumor in the dorsal, another one with a tumor in the dextral, another with a tumor on the central, and another one with a tumor in the sinestral position. This is in order to evaluate the performance of the system depending where the tumor is standing. In this case, the red circle illustrates the location of the tumor. We performed these experiments using our previous generation system, which is a bench system developed here in-house. Due to physical plant constraints, we needed to put a container to prevent the spillage of matching medium, which in in the case of this photography was canola oil. This was done with the first iteration of our antenna. For the second antenna that we developed, the matching fluid was no longer needed. We were able to obtain images with, in air, which is quite surprising, because up to this point most of the experimental systems require matching fluid in order to get any kind of meaningful data. This is a photo of the materials that we use in the Phantom. To the right we have a TX151 patch. This is a synthetic compound which is quite useful in the fact that by varying the amount of water, you can adjust the electric properties. It's the electric properties. Sorry. By playing with it, we have managed to get structures that mimic quite well both dense tissue structures and skin. And to the right is Parex bubble. The Parex bubble is filled with water and fructose, which is used to emulate the electric properties of breast tumors. This is a leap forward for us, because when we first started, we went from metal in the very early stages, which is not realistic. Then we went to blueberries. Scientists in University of Manitoba suggested that since blueberries have a high amount of water and fructose, and they are also used in ultrasound to emulate tumors, we should try them. And after some trial and error, I found that the blueberries that work the berries are the Saskatoon berries, Atrechalian berries, but they don't work as well. And from there, I went to torture my grad students, in the sense that I came with the brilliant idea of using bubble wrap and injecting it. And that didn't work well, because there's very little, there's almost no, there's only one kind of crazy glue that can be used to seal those, and my students became very good at it, at the point that I think that they can teach a kindergarten class with no problems at this point. Then they had the brilliant idea of me stop bugging them, and we went to the glass blower in the chemistry building, and she made these beautiful Parex bubbles that we just fill and seal using silicone. And since we have to break them at the end, they stab the dense tissue structure quite well, and they stay in their place, which is quite a significant achievement in phantom fabrication. This is just a simple table with the dielectric properties of the materials that we use for our phantom. For fatty tissue, we use glycerin, which has been used by previous studies to emulate fatty tissue. And by varying, as I told you before, the amount of water in the TX151 water mixture, we're able to obtain either dense tissue structure or skin. We use a multi-static scan protocol mostly because, as I mentioned before, it allows to get a higher contrast on the reconstruct images. The contrast difference is in the order of 2 to 1 when we use monostatic in comparison when we use a multi-static scan protocol. We quantified our data using the following metrics. We use the signal-to-clutter ratio. Essentially, we segmented the final image. We extracted the region with the highest value on the image. We calculated the variance of the rest of the image, which is given by sigma, and T is the energy of the strongest reflection region in the image. We also quantified the spatial error for both the dense tissue structures and the in the control group and the tumor in the data sets that contain a tumor. We calculated this by essentially taking the absolute value of the location of that particular signature in the image and compare it with the location of the tumor or dense tissue structure in the experimental setup. We also quantified the tumor to fibroventricular ratio using a very similar approach. We obtained the location of the tumor in the energy of the tumor in the reconstructed image, and we calculated also the energy of the most prominent dense tissue structure. And finally, by obtaining the difference of those energies and dividing it over the variance of the background, we calculated the contrast to noise ratio. This is the control group. In this case, we have the 3-6 phantom. There's a tumor, and I overlaid transparent green circle so you can appreciate where the location of the dense tissue structures is. In the first experiment, I overlaid the location of a red circle so you can see the response from the tumor, which is consistent with the location of the fructose water bubble in the experimental setup. And you can see, due to the fact that we have now a direct illumination when we're in the dextral support, the energy of the tumor response more than doubles. If we put the tumor on the dental support, now the energy goes back to around 0.001 milliwatts. We have some spatial error as well. In the majority of the experiments, the spatial error was no larger than 5 millimeters, which is around half an order of resolution of what we have in the system. We use a bandwidth of 1.5 to 6 gigahertz, which gives us an average spatial resolution in the system of 1 centimeter. And finally, when we have tumor on the sinestral position, we're not able to see anything. The energy levels of the dense tissue structures are similar to the ones in the control group. This is mostly caused because there's no direct illumination pattern, illumination position with the, mostly because the dense tissue structure is blocking the tumor. And when we illuminate from the other side, we have high losses in the glycerin that doesn't allow us to reconstruct proper tumor signature. The losses in glycerin for the particular bandwidth that we were using were around 4.5 decibels over centimeter. So given that we use a phantom with a diameter of 11 centimeters, we were coming really close to the noise floor level. This is very similar to results that other groups are observing whenever they don't have a direct illumination pattern on the tumor. As we can see in all the experiments, the signal to closure ratio was above 10 dBs. We quantified the contrast of the tumor to fibroventricular ratio on the experiments where we could actually discern a tumor, and in both cases, and in the majority of the cases, they were above 3 dBs. What's the significance of 3 dBs? Well, in radar engineering, you basically use the 3 dB point as a benchmark in order to show that the energy of your target signature is more than double of what you expect from your noise. This is used as a very minimum that you need in order to define a constant false alert ratio. But how is this useful? Are these results good or not good? What do we make of this? Well, we compare our results with what the leading two groups in the area are doing. So far in experimental studies, using similar phantoms, these are we report signal to global ratio because we define the background, those are background responses as clutter because they're not truly noise in the strict sense of the word. They define it as noise, so I use the common nomenclature of signal to noise ratio. We have signal to noise ratio for our direct illumination, for our target that was directly illuminated, which was the target in the dextral position, of 19.5 dBs. A similar study from the University of Calgary found that their technique yields images with a signal to noise ratio of 9.5 dBs, and a group from the University of Bristol, which is the one that has the most advanced clinical system in the world right now, found that they achieve in average between 3 and 2.6 dBs in phantoms. They haven't quantified any kind of contrast metrics in their images, and the spatial error for ultra systems is in the order of 4 to 5 millimeters. When it comes to comparing other parameters such as image reconstruction time, not even using the GPU techniques, this is only using standard MATLAB code, we're able to obtain images on 0.82 seconds. The University of Calgary group, the formation of a single 2D image takes around 100 seconds, and the same for the University of Bristol because they use time domain approaches. We are the only group trying to use frequency domain approaches to form images. We have the longest scan time, of course, because our system is probably the cheapest. We have a scan time of 30 minutes. We also use the largest number of scan locations. We use 144 scan locations. The University of Calgary started doing that as well, but then they cut it to around 40 to 80 locations, depending on the experiments. And the University of Bristol has a system that has a very high-tech switching matrix, which allows them to finalize a scan within 2 minutes. But on the other hand, our system was made with a cost under $24,000. We have a very cheap vector network analyzer. That's the main reason. The driving factor of the cost of the system is the quality of your RF instrumentation. The University of Calgary has a moderately priced system, which is about $60K, mostly because they have a higher-end vector network analyzer. And the University of Bristol system costs between $350 and $500,000. This is mostly because they have probably one of the most advanced vector networks analyzers in the world, whereas the standard vector network analyzer is usually fitted with 2 ports, sometimes 4. Their system has 32 ports, and as the standard vector network analyzer is capable of making a scan within half a second, 1 second, this system can scan the 64 points, the 64 ports within 200 to 300 milliseconds. So it is a very advanced piece of equipment. But one thing is that due to the work that we have been doing in the last couple of years in the aspect of antenna development, we no longer need a matching fluid, which simplifies the mechanical and the mechanical design by, I would say, it saves us a lot of. It's difficult to quantify, but it saves us a lot of headaches. Mostly because you don't have to account for the fact that you have a tank full of fluid that is going to spill, or components that are going to eventually fall into the grate due to the fact that fluid is going to get inside of them. The system at the University of Calgary uses canola oil as their matching fluid, and the University of Bristol has a proprietary matching fluid that has the electric properties very close to glycerin. This is the system that we have developed at the non-ionizing group. It's essentially a patient bed with 2 instrumentation racks underneath. On this side, we have all the radar equipment, And on this side, we're collaborating with the electromagnetic imaging group here at the U of M, and they are performing scans using using some of the microwave instrumentation. This is the first system in the world that is capable of collecting both microwave imaging modalities on the same place. We consider in this design the use of solid-state sensors. We have been collaborating with the spintronics sensors group here at the U of M, and I will show you a little bit more about that in a second. But this is a very novel sensing technology that can allow us potentially to get rid of large antenna arrays. The part that we like the most, as I told you before, about this system is that we no longer need a matching medium. This is what's ABS? What's the name of the CAB container, which we use basically for phantom experiments. It is modeled after the actual dimensions of a human breast, and this use of antennas in air has had a wide number of applications, from system design to patient comfort to system maintenance, mostly because if something breaks, we don't have to drain the tank, and we don't have to clean every single structure, as it was the case when we had antennas immersed in oil. The whole operation of the system is vastly simplified. In the last 2 years, we have been collaborating with the spintronics sensor, with the spintronics group at the Department of Physics, and we are in the verge of attempting something really novel. It's the use of this type of sensor, which is called a spintronic sensor, on actual human on actual patients with breast cancer, hopefully later this year. This has allowed us from potentially going from an array of antennas, which are around 10 to 12 centimeters, to only one antenna and a bunch of these small sensors that are 500 micrometers. As any RF professional can tell you, when you put a bunch of antennas really close, you need to, as it will be a microwave radar system, you need to be quite careful due to the fact that you're going to have interference patterns in antennas that are going to limit the number of antennas that you can put into the array. With these sensors, that's no longer the case. This technology allows us to potentially introduce a very dense populated array that will give us high quality images. This is a comparison between an image obtained using solid-state sensors and one obtained using our current antenna technology. We can see that we have considerably smaller point spread function. We're still testing it to try to assess its specificity and sensitivity compared to our conventional antennas. The use of solid-state sensors has opened the possibilities to an area that we have been exploring theoretically in the last couple of years. What if images are not really needed? Can we be able to detect cancer only by using the responses that we record from the breast structures? Well, in the last decade, a couple of groups in Europe have thought so. And by using artificial intelligence techniques, they have produced some results on simulations that show the feasibility of this approach. For this idea, we tried to elaborate a more complex project, and we came with a proposal that was finally backed up by grand challenges and encompasses the creation of a portable breast microwave radar system that is not going to generate any kind of images. It's basically going to use the backscatter signals from the breast structures to determine if there's a tumor or not. The main goals of this project is that we should be able to develop a portable system, ideally capable to be carried in a backpack. It will be really cheap because essentially it is meant for widespread use by third world countries, or by use in remote areas. It needs to be quite rugged for that particular reason, because there's going to be very little access in terms to specialized personnel, and ideally it should be very easy to use. It should be so easy to use that a person with minimal training or no training at all should be able to scan herself. Ideally, the idea is for the patient to be able to scan herself. Is this actually possible? Are we having a crazy dream here? Well, it has been proven that apparently high-tech equipment can be operated if designed properly by people with minimal training. A good example is what happened in Mexico 2 years ago. There was a community a community of 200 people with only one phone. And of course there was quite a turmoil, because as the men in that community started immigrating into the United States, everyone in the community needed to share the same phone, and it was causing some chaos. So ONG and a group of engineering students at UC Santa Barbara installed an open source cell phone network at that particular town, with help from some of the US carriers in terms of satellite access. But they designed the equipment and they trained the personnel in very rudimentary maintenance techniques so they could keep the network going. And so far it has been a success. From a town that had only one line, they have 16 lines right now, shared between all of them, and it is still running. Similar projects are right now ongoing in India, and some of them actually started by a piece of equipment developed at the Burning Man Festival. I don't know if you have heard about it. It's kind of a hippie festival in California. They don't like the fact that they had it to subdue to traditional carriers, so they developed their own cell phone network for the, yeah. Okay, so I'm gonna go quite quick over this. Basically, the idea is to use signal classifiers to basically differentiate between breast and malignant breast structures in the breast. Basically, we got different scanning patterns from benign and malignant structure. The benign structure usually has a smooth shape, whereas a malignant structure has an spiculated form. What we do to basically train our classifier, we use a feature component obtained using principal component analysis. This mathematical technique is basically used to extract the main features of a data set. Without going into much detail, this technique is quite used in several fields, such as computer science all the way to neurobiology. The idea is to decompose a very complex data set into its basic features. A very easy way to see it is essentially we have an ellipse, rotated and escalated ellipse on an S1 and S2 feature space, and if we apply a PCA procedure, we will be able to obtain its major and minor axis and the escalation factor in a different feature space. This is a very simplistic way of saying it. Essentially, the idea is to reduce dimensionality and obtain series of vectors that give us the inner workings of the phenomenon that generated that particular signal. I'm going to skip these because I'm short of time. We use two types of discriminants to perform the the analysis on a series of data sets collected from experimental phantoms. The first one are linear discriminants, and the second one, as its name says, is quadratic discriminants. It basically, the main difference between both of them is the nature of the discriminant lines that separate the different classes in the feature space. To avoid overfitting the data, we perform a cross-validation process, which essentially means that we train the classifier using a given series, a given number of data sets, and we evaluate its performance using a different data set. We kept switching the training and evaluation sets in order to avoid the overtraining of the data that will result on a loss of performance. We created benign structures and malignant structures ranging from 13 to 40 millimeters in diameter. We recorded those using our benchtop experimental system. And we only use the 30 most prominent principal values, mostly because, as this chart shows, after we went past the 30th value of the 30th PCA component, we saw no further improvement we saw very little improvement on the accuracy of the classifier. The results are quite promising. We have a detection rate of 87% for the linear discriminant, and 89% for the quadratic discriminant. When it comes to check, when it comes to size, we have one that is well, for the linear discriminants is 92, and for the quadratic discriminants on experimental data is 94. Why are we getting better results on experimental data sets compared to simulated data sets? Well, it is mostly because the principal component analysis is based on the analysis of the covariance matrix of the data set. And since the experimental data is shown to have a bigger variance, mostly because it is collected at closer distances compared to the simulated data sets. Simulated data sets made a plane wave assumption on the irradiated that reduced that variance. The PCA algorithm is capable to work with these inner mechanics and improve and give us an improved classification index compared to the simulated data sets. We're still having an issue in the sense that if we want to classify wood size and shape, we're still getting noticeably worse results than in the case when we only want to classify either size and shape. This is work in progress at the moment. But we're looking towards sending a system that is not going to perform any diagnostic functions later this year to Africa. It is just only to evaluate the potential of very simplistic solid-state sensor system in which a volunteer is capable of scanning herself. We want to see if that principle is actually feasible. This is basically a demo system. It is only going to be used to assess the subject experience. Well, I hope that I have given you an illustrative introduction to the breast macroaggregator. The challenges are still many, but we have been doing some work here at the U of M that is quite promising in my opinion, and we have been so lucky that some major agencies have helped us to accomplish these goals, and both the classification approach and the holography techniques will be tested later this year on larger scale, well, in a clinical trial. The holography technique will be tested with actual patients that have cancer, and the classification technique will be tested for its actual feasibility first in phantoms, and in the sense of the proof of principle that a subject can scan herself. And I would just like to thank these wonderful people, which without their help, this research would have not been possible. I would like to thank the people at the machine shop who make a lot of our systems at Cancer Care Manitoba, and our research is supported by these agencies. I think I went 5 minutes over.
Yeah, we do have a few minutes for questions if anybody has.
Yes.
Thank you, Daniel. Very interesting, and it's very encouraging to see the progression of your stuff really doing well for years. Can you explain a little more about the difference between the monostatic and the what do you call it, multistatic?
Bistatic.
Yeah, I'm trying to understand, like, how do these things differ in terms of eventually the different results you're getting?
I forgot to mention this, Dr. Sharif. This is bistatic, and the first one is monostatic. What we're doing is, it's not like you have to do one or the other, you can do both. We call that approach multistatic.
Okay.
We're fusing both. In monostatic, essentially what happens, you have, you know that your antenna is, that your receiver and transmitter are at the same location. So the nature of the frequency spaces are simpler. Instead of having a signal that is function of, well, you have a signal that is function of the signal travel time and the angular location where you record it. So the nature of the frequency space is simpler. When you arrange your system in a bistatic setting, you have 3 variables. You have the signal travel time, you have the transmitter location, and the receiver location. These data sets are a little bit more complex to reconstruct, but they give you the advantage that you have what is called in radar, probably there's a similar term in ultrasound, spatial diversity. Basically, this is the same technology that is used to detect stealth fighters. In the World War, it was the F-117 was designed in such a way because at that time most of the systems, most of the radar systems have a given separation between the transmitter and receiver that made them blind to the particular radar cross section of the F-117. What the Iraqis started doing is using radio towers in other towns as passive radars in order to detect the bombers. So that's why the Americans came with the V2. So it is a similar principle. You're using spatial diversity to try to characterize different reflections from the tumor and increase the specificity.
So can I understand that as in the bistatic, for example, you're introducing more asymmetry,
exactly.
And that asymmetry is basically allowing you, I would say, better quality images and better...
more information.
Yes, you're having more spread in your
in my case space.
Exactly.
Yes.
Yeah.
Yes.
Can you explain about 2 features that distinguish from the image? One is the size, another one is the shape of tumor, right? Do you think these 2 features are reliable enough to classify tumors from, for example, something like a calcification in the breast?
That's what we're trying to find, actually. Right now, we're not using. I can say it. We're not using the size and the shape as the, well, let me put it this way. Right now, to the best of our understanding, that's the best. Those are the 2 best features that we have to classify tumors. Mostly because of the way that the tumor actually develops. When the tumor is benign, it tends to have these smooth shapes. There's how you call it? There's cases that not fall into that category, of course. But the ultimate purpose of this system is to be a kind of warning system that is going to tell the subject in a remote community that she should check herself because there's something abnormal. we're not extracting data from the image.
Classification are irregular in the shape.
Yes. We are not extracting the features that are fed into the classifier from the image. We're extracting them from the actual raw data set.
Okay, I think in the interest of time here, we'll break it off. But if anybody has